In this lesson, we're going to take a look at field lines. Now, field lines are a way for us to represent field forces, which are forces that act through a distance. Field lines give us a visualization of what happens. So imagine I have a positive charge just hanging out here in space. Now, that positive charge actually energizes a region of space around it. And so if another positive charge were to come next to it, there would be a force on this charge. Those two charges would repel, and this one would be pushed away. And that's actually how we describe a line of force for a force field. We say, okay, this line points away from the charge because that's the way a positive charge would be pushed. And the more field lines there are, the stronger that electric field is. And so these two forces don't have to touch because these two charges don't have to touch because this particle is energizing this region of space around it. Now, one of the things we look at is how strong is this field? And the answer is it depends. It depends on how big this charge is. If I make that charge bigger, then this field gets stronger. It also depends on how close we are to that charge. If we're this far from it, you'll notice these field lines can cover a whole bunch of area. There's not very much open area without a field line. If we go a little bit further out, then the gaps between the field lines get much bigger, and that's indicative of the fact that that field is getting weaker. So the farther you are from the charge, the weaker the field. The bigger the charge, the bigger the charge, the stronger the field. Now, we can also look at field lines for combinations of things. So it's not just charges that have fields. There's masses create gravitational fields, and magnets create magnetic fields. Charges create electric fields. And so if we have a magnet, just a bar magnet, it has a north pole and a south pole. And even if we broke it in half, we'd end up with two smaller magnets that both have a north and a south pole. And magnets create magnetic field lines that emanate from the north pole and wrap around and come into the south pole. So you should put arrows on your magnetic field lines in the way that it goes, and that's the way a compass will point if we were to put a compass in the field. This is the way a positive charge gets pushed if we put a positive charge in the field. That's why a negative charge has, if that's our fields, we got a negative here, this is a negative charge, then these lines are going to go towards it. Okay? Now, this magnet creates these field lines that go around it. Now, what about a horseshoe magnet? A horseshoe magnet is bent. So we still have a north and a south, but now to emanate from the north and go to the south, these field lines just go straight across, and you'd still get some bulging around like that. And you can do a similar thing with charge. If I had a positive charge and a negative charge, the electric field lines from the positive would go straight towards the negative, and so we would get something that looked like this. They're trying to go away here, and then they get pulled back down in here. If we had two positives, that's a little bit different because field lines can't cross, so this field line would get pushed, and this field line would get pushed. And so if we put something right in the middle, there's no electric field there. It would be stuck. It couldn't go either way. And so you could also get field lines that go this way. So if we're a little below, it's going to get shoved down. If it's a little above, it's going to get shoved up. But if it's right in the middle, then there is no net force because those two fields cancel each other out.